Aloha! I'm standing on top of Waikiki Beach, the world's most popular tourist destination. In the background is Diamond Head Mountain, the remnant of an old volcano that blasted its top off long ago. Now, the Hawaiian Islands are a pretty special place, and out here we're separated from the rest of the world by about as far as any of the islands on this earth are. But what are the Hawaiian Islands really? I'll tell you. They're a chunk of solid rock that start at the bottom of the sea, extend up through the liquid water, and into the gaseous region above the surface of the water. Now, water is so very important here in Hawaii. So many activities center around it. People spend their time fishing in the water, swimming, surfing. You might be able to tell what my favorite activity is. Well, in today's lecture, we'll discuss all three phases of matter, including the liquid phase. So join me for this. In today's lecture, we discuss phases of matter, and in particular, the relationship between intermolecular forces and phases of matter. Let's take a look. Here are the three phases of matter. You have your solids, liquids, and gases. Solid particles are close together. In fact, they are locked together. Solids are rigid. The particles are not flowing around. Liquid particles are also held close together. However, liquid particles have the freedom to move around. Gas particles are basically flying around independently of one another. Gases are very different from liquids and solids in that aspect. The particles are far apart. Some other distinguishing properties between these phases are, well, the density. Solids and liquids have a much higher density than gases, much greater mass per unit volume than the gases do. Shape. Solids have a defined shape. They're rigid. Liquids and gases, on the other hand, basically take the shape of their container. Compressibility. You cannot really compress a solid or a liquid. However, it's pretty simple to compress a gas. The particles are far apart enough that if you increase the pressure, you can reduce the volume of a gas. You might remember Boyle's law says that doubling the pressure, the volume drops to 1/2 of its previous value. Intermolecular forces are apparently strong enough to hold liquid and solid particles together, but not so much the gas particles. What's going on there? Well, to better understand the differences between these three phases, we need to take a look at what happens when you change from one phase to another. Say, changing from the solid to the liquid phase. Now, we know that one way to get from a solid to a liquid is by melting it, by heating it up or increasing its temperature. And what you're really doing when you heat something up is, of course, you're increasing its temperature. Now, what is temperature, though? You see, temperature is a measure of the molecular motion. Now, we understand when something feels hot versus something else feeling cold, okay? But if you were to break out your, say, molecular magnifying glass, you could actually see those particles in the hot object moving around more quickly. If it's a solid, that means the particles are vibrating more quickly. There's more molecular motion in hot substances versus cold substances. Cold substances, everything's moving more slowly. You see, we just can't see that with our eyes, but that's what's going on. So when you have a solid where the particles are held rigid, those intermolecular forces are strong enough to lock the particles together. As you heat a solid up, you're increasing the molecular motion, and eventually, if you heat it up enough, the particles will break free from that locking intermolecular forces, and they'll begin to flow past one another. Now, the particles still feel each other, the intermolecular forces are still there, but at least they can move around a little bit. If you continue to heat a liquid up, you will increase the molecular motion that much more that eventually the particles will completely break free from one another, and you'll have yourself a gas. If you continue to heat up your gas, the particles just fly around that much more quickly. You can go the other direction. If you cool your gas back down, the particles slow down, and eventually as they approach one another, the intermolecular forces make the particles feel each other. And if you cool it down that much more, eventually the particles stick together and you recondense your gas back to a liquid. And if you cool your liquid back down, eventually the intermolecular forces really take over and the particles lock in place, and you'll have yourself a solid. Okay? Now, another way to change phases, at least between the liquid and gas phases, is by changing the pressure. You can boil a liquid by reducing the pressure. Perhaps you recall that at the top of a mountain, where the atmospheric pressure is less, it's much easier to boil liquid. At the top of a mountain, water may boil at 85 degrees Celsius, whereas at sea level, it boils at around 100 degrees Celsius. By reducing the pressure, you can cause water to boil. Well, what you're really doing when you change the pressure is you're really changing the proximity of the particles. Let's take a look. Suppose you have a gas trapped inside of a piston. That gas has a certain pressure. If you increase the pressure on that gas, say by dropping a couple of weights on top of this piston, you will lower that piston and increase the pressure of the gas. And you're basically causing the particles to become more close together. And you can really squeeze a gas into a liquid by increasing the pressure just enough. And if you release that pressure, you can allow the liquid to evaporate back into the gas. Now, we'll take a closer look at boiling a little bit later in another video, but for now, increasing the pressure, you can basically squeeze a gas into a liquid. That's another way you can change the phase. So what is this mysterious glue that holds the solid and liquid phases together? The answer, I think you'll find, is rather simple. It all arises from the fact that positively charged particles are attracted to negatively charged particles. Let's take a look. Suppose you have a positively charged particle and a negatively charged particle separated by a distance r. Then Coulomb's law tells us that there is a force of interaction between them. They're attracted to each other through a certain force. Now that force is described by this equation, which is really a statement of Coulomb's law in mathematical form. The force is equal to a constant times the magnitude of the one charge plus 1 times the magnitude of the other charge minus 1 divided by the square of the distance between them. So you see, the larger the magnitudes of the charge, the stronger the force, and the larger the distance between them, the weaker the force. Okay? Now, we remember from before that negatively charged particles attract positively charged particles. Okay, nothing really new there. Well, atoms and molecules in particular are composed of positively charged protons and negatively charged electrons. So they have within them that ability. Let's see how it works. Molecules are composed of protons, neutrons, and electrons, of course. Now, the electrons, being much smaller than the protons and neutrons that are in the nucleus, can move around. And sometimes there are more electrons on one side of the molecule than on the other side. And when that happens, the molecule ends up with a negative end and a positive end. You see, water is a prime example. The oxygen in the water molecule is electronegative, meaning it pulls electrons towards its end of the molecule. And when it does that, water ends up with a negative end and a positive end. You say that water is polar. It has a dipole that points up towards the oxygen. Now, why does it do that? Why does the oxygen pull electrons towards its end of the molecule? Well, the answer to this is rather simple too. If we take a look at the periodic table, specifically the top right-hand corner of the periodic table, these elements in the triangular region are all electronegative, meaning that they all tend to pull electrons towards their end of the molecule. And the reason is because they're pretty close to the noble gases in terms of how many electrons they have. And we know that the noble gases are stable elements. What's really stable about them is the number of electrons. Their electron configuration is a stable configuration. And these elements, being close to the noble gas, tend to attract electrons towards themselves because they're trying to get the same electron configuration that the noble gases have. You see, oxygen is only 2 electrons away from neon. So whenever there's an oxygen in a molecule, it tends to pull electrons towards its end of the molecule in order to be like neon. And same with the other elements in this region. You see, the metals, on the other hand, on the other side of the periodic table, tend to repel electrons for the same exact reason. But the nonmetals tend to attract electrons. Fluorine is the most electronegative element on the periodic table, and oxygen the second most. Okay? So water does have a negative end and a positive end because it has the oxygen. And when water is cooled down, the molecules, remember, move more slowly. And when you cool water down enough, the molecules end up feeling each other. That dipole within one molecule feels the dipole in the next molecule. And what happens is the water molecules end up lining up with each other. You see, the negative end of one water ends up sitting next to the positive end of the neighboring water. And it happens in like a chain reaction. The waters all line up. And that's what ice looks like. It's a very ordered configuration of water molecules in which they're all kind of lined up with their dipoles interacting with each other. Okay? Now, a similar situation occurs in solutions of ionic compounds. If you have a solution of sodium chloride, now we know sodium chloride dissociates when it dissolves in water. The cations become separated from the anions. Well, the reason that happens is because of water being attracted to cations and anions. You see, water is very good at pulling cations and anions apart because of the dipoles in water. So when sodium chloride dissolves, the cations are surrounded by a bunch of water molecules with the negative ends pointed toward the cation. And the anions are surrounded by a bunch of positive ends of water molecules. And that's what ionic solutions look like. Intermolecular interactions can be classified into 3 major types. The first type is the dispersion interaction, also called the van der Waals interaction. And these interactions are temporary dipoles that interact with one another. If you have a molecule, the electrons in that molecule being able to move around relative to the nuclei sometimes will move towards one side of the molecule more than the other side. So by chance, there might happen to be more electrons on this side of the molecule than on that side of the molecule. And in that case, you would have a temporary negative side and positive side. In other words, a temporary dipole. And a temporary dipole in this molecule can induce a temporary dipole in the neighboring molecule, which can induce one in its neighbor molecule, and so on. And so you can have like a chain reaction occur. Now, dispersion interactions are rather weak. However, all molecules exhibit dispersion interactions. So examples are methane and benzene. The next type of interaction is the dipole-dipole. Now, in order to have dipole-dipole interactions, there has to be a permanent dipole. So not all molecules exhibit dipole-dipole interactions. However, examples are CHCl3 and HBr. And these interactions are stronger than the dispersion interactions. The third major type is the hydrogen bond. And hydrogen bonds are really special type of dipole-dipole interactions in which nitrogen, oxygen, or fluorine is directly bonded to a hydrogen. So there has to be a dipole already, and there has to be N, O, or F directly bonded to an H. Then you can have hydrogen bonding occur. So the molecules that exhibit hydrogen bonding are a subset of those molecules that exhibit dipole-dipole interactions. An example of a substance exhibiting hydrogen bonding is water. And these are very strong interactions, stronger than the other two types. Now, a special note needs to be made. Stronger intermolecular interactions means higher melting and boiling points. You remember if you have, say, a solid substance in which the particles are locked together through intermolecular interactions, rather strong interactions. In order to break those interactions, you need to heat the substance up. You need to shake the molecules, cause more molecular motion. And the stronger those interactions are, the more the substance needs to be shaken, the higher the temperature needs to be raised, in other words. So if a substance has, say, hydrogen bonding in it, then it's going to be rather difficult to break those interactions. And the melting point will be higher than it would if the substance only had dipole-dipole or dispersion interactions. And the same sort of argument applies towards the boiling point. If a liquid exhibits rather strong interactions, then it will be rather difficult to break those interactions. The boiling point will be higher. All atoms and molecules contain electrons, therefore they all exhibit dispersion interactions. Consider the atom helium. In one instance, or one frame, the two electrons of helium might be on opposite sides of the nucleus. A little while later, in a second frame, the electrons have moved around, but they're still on opposite sides of the nucleus. Now, in a third frame, the electrons may find themselves on the same side of the nucleus, therefore the atom has been polarized. Now, this instantaneous dipole that has formed can induce a dipole in the neighboring helium atom, which can do so again. So helium does exhibit dispersion interactions. Now, molecules are larger than atoms, and they contain more electrons. And the more electrons there are, the larger the ability for dispersion interactions to arise. And that's the trend that we see. The larger the molar mass of a molecule, the more electrons there are, and the stronger the dispersion interactions. If we compare the alkanes, methane, which is CH4, ethane, C2H6, and propane, C3H8, we see that trend where propane has the strongest dispersion interactions. How do we know that? Well, propane has the largest boiling point. That trend also continues if we examine even larger alkanes. If we compare the boiling points of pentane which is C5H12, hexane, heptane, octane, all the way up to nonane, which is C9H20, then we see that the boiling points increase for these N-alkanes. Now, the molar mass is not the only determining factor in the strength of dispersion interactions. The shape of the molecule is also important. And we can see that by comparing N-pentane with neopentane. These compounds have the same molecular formula. However, N-pentane has the carbons attached in a linear chain, whereas neopentane has a carbon in the center tetrahedrally surrounded by the 4 other carbons. Now, neopentane is a more spherical molecule, and this molecule does not have as much surface contact with a neighboring neopentane as an N-pentane does with a neighboring N-pentane. There's more surface-to-surface contact between the N-pentanes, therefore stronger dispersion interactions. And N-pentane has a much higher boiling point than neopentane, 36.1 degrees Celsius compared with 9.5 degrees Celsius. In order for compounds to exhibit dipole-dipole interactions, there needs to be a permanent dipole present in the molecule. Now, to determine whether or not a permanent dipole is present in the molecule, it might be a good idea to go ahead and draw the structure. Let's take a look at a few examples. The first formula is CH4, and we know the structure for CH4. It's a tetrahedral structure where carbon is surrounded by the 4 hydrogens in a symmetric fashion. Now, there are not even any electronegative elements present in this compound, and even if there were, it's a totally symmetric molecule. So this is definitely a nonpolar molecule. Now, it still exhibits dispersion interactions. However, there are no dipole-dipole interactions present in methane. The next example is carbon tetrachloride. And the structure for CCl4 is similar to that of CH4. It's also tetrahedral, but now the 4 positions are occupied by electronegative chlorines. However, the chlorines are totally symmetric with respect to each other, and it's kind of like a 4-way tug of war, and the electrons end up not being pulled anywhere. The bond dipoles totally cancel off, and this is a nonpolar compound. CHCl3 is also tetrahedral, and the structure is similar to CCl4. However, now one of the positions is occupied by a hydrogen. And here, the 3 chlorines on the bottom end up pulling electrons towards their end of the molecule, and this does have a molecular dipole, so it is a polar molecule and exhibits dipole-dipole interactions. The next example, C2H2F2. Now, this formula is somewhat ambiguous because there are multiple ways to draw the structure. You call each of these possible structures geometric isomers. Now, the first geometric isomer for this compound has the 2 carbons double bonded to each other, and the carbon on the right is also bonded to both of the fluorines. So here, both of the fluorines are on one side of the molecule, and there is a molecular dipole pointing that way towards the middle of the 2 fluorines. So it's polar. The next geometric isomer has a fluorine attached to both of the carbons. However, they're on the same side of the molecule, and the electrons are now pulled towards the side of the molecule. So it's also a polar molecule. The dipole may not be as strong as when the fluorines are pulling towards one end of the molecule. However, they're still pulling to the side, and there is a dipole here. So it's polar. The third geometric isomer has a fluorine attached to each carbon. However, now the fluorines are pulling in opposite directions, and the dipoles cancel off. So there is no molecular dipole, and the compound is nonpolar. The last example, CH2F, CH2F, the formula being given like that, again, because you're trying to be guided towards the correct structure. Here's the structure for this compound. Each of the carbons gets a fluorine, as indicated by the formula. Now, although it looks like the bond dipoles cancel each other off, the molecule is actually polar. Why is that? Don't forget that single bonds can rotate. And sometimes this fluorine is pointing in the same direction as the other fluorine. So this molecule does have a dipole associated with it. The hydrogen bond is a very strong dipole-dipole interaction. To have a hydrogen bond, there needs to be either nitrogen, oxygen, or fluorine directly bonded to hydrogen. Now, what is it about these three electronegative elements and hydrogen that makes the dipole so strong? Well, we can answer that question by comparing two different but related compounds. Here we have H2O and H2S. Now, the structures of these molecules are the same, and that's because sulfur is right below oxygen on the periodic table. They are both electronegative. These molecules have a negative end and a positive end. The main difference is that oxygen is much smaller than sulfur. And a small electronegative element, when it pulls electrons towards its end of the molecule, you end up with a smaller and more concentrated, powerful negative region on the molecule, as opposed to the sulfur. When it pulls electrons towards its end, it's a much larger negative region on the molecule. Okay? Smaller negative charges are more powerful than larger negative charges. Smaller charges can come in closer contact with one another, so they are much more powerful than larger charges. All right? And that's the main difference between the nitrogen, oxygen, and fluorine as opposed to the other electronegative elements. You remember that the electronegative region on the periodic table is this upper right triangular region. And the nitrogen, oxygen, and fluorine are those elements that are in the second period, those smaller electronegative elements. Okay? Now, when you have one of these small electronegative elements attached to hydrogen, well, what happens is that small, powerful negative end of the molecule pulls the one and only valence electron away from the hydrogen, and when that happens, the proton on hydrogen gets exposed. So you end up with a really small positive portion of the molecule as well. Small negative region and small positive region. That makes for an especially strong dipole. Now we can see the effects of hydrogen bonds by comparing compounds that hydrogen bond with those that do not. If we take a look at dimethyl ether and ethanol, these compounds have the same molecular formula. The main difference is that the ether has the oxygen connected to two carbons, and the ethanol has the oxygen connected to a carbon and a hydrogen. So the ethanol can hydrogen bond. And the boiling and melting points on the ethanol are much higher than those on the ether. It's because of the strong hydrogen bond interactions. Now, with knowledge of the intermolecular forces, we can better predict the order of boiling points and melting points on compounds. Let's take a look at another example. Here you want to arrange the following in order of increasing boiling point. And the compounds are sodium chloride, ethane, which is a hydrocarbon, ethanol, which we've just seen, and CH2F2. Now, to arrange these in order of their boiling points, we really need to arrange them in order of the strength of their interactions. Now, sodium chloride is kind of in a class of its own. It's a full-on ionic compound, and ionic compounds have real positively charged cations and negatively charged anions interacting with one another. That makes for a tremendous interaction force. And ionic compounds always have a much higher boiling and melting point than molecular compounds. Okay, so this one should have the highest boiling point. Now the others can be ordered by their intermolecular interactions. Ethane is a nonpolar molecule, and it should have the weakest interactions, dispersion interactions, that's it. The ethanol, we've already seen, has hydrogen bond interactions. And the CH2F2 has dipole-dipole interactions. This one does not hydrogen bond. And you can see that if you draw the structure. This is a tetrahedral structure where all four of these elements are connected to the carbon. They're not connected to each other. Okay? So the nonpolar should have the smallest boiling point, and the one with the hydrogen bond should have the greater boiling point. And you end up with this order. Many physical phenomena are explained by intermolecular interactions. Let's take a look at a couple. The first is liquid-liquid solutions. Now we know from experience that some liquids dissolve each other and other liquids do not. Water and alcohol dissolve each other and are said to be miscible, but oil and water do not and are said to be immiscible. Now the difference between these two mixtures are the intermolecular interactions of the components. You see, oil is a nonpolar fluid, and it only exhibits dispersion interactions. However, water is very polar and can in fact hydrogen bond. And those hydrogen bonds between the water molecules are very strong interactions. And that's what kind of pulls the water molecules together. You see, oil doesn't have that. It only has dispersion interactions. And the oil does not want to mix with the water because doing that would disrupt those strong intermolecular interactions between the water phase. So the water kind of sticks to itself, leaving the oil in a separate phase. Now, alcohol and water, on the other hand, are both very polar fluids and have the capability to hydrogen bond. And the hydrogen bonds on the alcohol interact with those on the water. And those interactions between these two molecules are what allow the fluids to mix together. This rule is described in the three simple terms: like dissolves like. Polar liquids generally dissolve each other, and nonpolar liquids do as well. Oil may not dissolve with water, but it should dissolve with gasoline, which is also nonpolar. The second application is protein folding. Now, proteins are long chains of amino acids that are connected together in a linear fashion. This is the amino acid residue glycine. The residue, it's what's left over after the amino acid connects to another amino acid. Okay? Now, amino acids have a couple of very electronegative elements, specifically the nitrogen and the oxygen. And this nitrogen, being connected to hydrogen, has the capability to hydrogen bond. So with a long chain of amino acids connected together in a very long molecule, Because this chain is flexible, you remember single bonds can rotate, and amino acids are basically a bunch of atoms connected together through single bonds. So this is a very flexible chain, and what happens is this chain can wrap around and in on itself. And that's because of the dipoles on one amino acid interacting with the dipoles on, say, an amino acid several units down the chain. Okay? Now, proteins typically form regular sort of shapes, and one shape is a helical type of structure called the alpha helix. And another one is where the chain sort of zigzags back and forth, and that's called the beta sheet. Most proteins contain these sort of motifs. Now, DNA also does a similar phenomena. DNA forms like a double helical structure. And what holds that double helix together are the intermolecular interactions between one part of the DNA molecule and another part. So it sort of twists in on itself. There are other applications that are explained by intermolecular interactions. We don't have time to go into them, but they are very interesting, and I'll just name a couple. Surface tension, where you can, say, float a paper clip on top of a water surface. Why is that? Well, it's because of the water molecules sticking together. That paper clip doesn't want to break those interactions between the water molecules. And another is capillary action, where water can travel up the surface of a tube. In this lecture, we've discussed in pretty good detail how intermolecular interactions work. And strong interactions can be difficult to break. Well, in our next shorter lecture, we'll be interested in how much energy it does cost to break these interactions. In other words, the energy cost to melt a solid or to boil a liquid. So I hope you join me for that.